Welcome to this year's vaguely Halloween-themed episode of Stand Up Maths. This year, for Hello Meme, we're going to have a look at this meme that says an infinite number of $1 bills and an infinite number of $20 bills would be worth the same. You've then got the username PopandLoopy and then a picture of the Scottish comedian Limmy. And that's actually from Limmy's video about which weighs more, a kilogram of steel or a kilogram of feathers.
You alright?
Don't get it.
One of my favourite videos on the internet. Do check it out if you haven't seen it. And Limmy does a lot of live streaming on Twitch. Also worth checking out. Here, they are just expressing confusion. And I looked into the history of this meme because it's been passed around a lot recently, which is why several of you sent it in to me. Thank you very much. And that original text is from a website called Just Shower Thoughts. PopandLoopy then took that and posted it on Tumblr, which is why you can see their name underneath. They added the screenshot of Limmy looking confused, and then another user, KurtDog, reblogged that on Tumblr, and that is where the comments kicked off. Since then, it's been, the screenshot's been taken of that, it's been posted to Reddit, but this original reblogging was on the 2nd of September, 2016. There you are, an old meme. And yes, there are a bunch of new comments from when it's been put on Reddit, but let's start by having a look at some of the original comments on Tumblr.
That's not true at all.
That's literally just the concept of infinity. I don't get it.
No, they both equal infinity in number. You just have way more single bills than 20 bills.
I liked this post until I started reading the comments.
I deck what all this means. It ain't though. Ask math, TM.
I'm glad someone finally thought to ask Math Trademark. And on behalf of Math Trademark, I'm going to answer, which is why I have these two stacks of infinite numbers of notes. Look at them go. I mean, from my point of view, they touch. A little perspective gag there for you. Now, I live in Europe, so I wasn't able to get real US dollar notes. I had to get local ones. And these are real, totally not from a prop hire place. I'd like to thank my Patreon supporters. They've literally provided this money. There you go. So these are £20 notes on this side over here, and these are €500 notes. Now, a pound and a euro, as of late, are roughly the same thing. And so instead of having $1 notes and $20 notes, where each note here is worth 20 times the other one, I happen to have notes £20 on this side, and these are worth 25 times as much. But the point is, every single layer in this, every note on this side, this one is worth 25 times as much. And that is true all the way up. So the question now is, if there are infinitely many of both of these piles, are they the same amount of infinite money, or are they different amounts? I like to get my head around it by imagining duplicating this pile, as in you take this pile and you start dealing them out. And because each of these are worth 25 times as much as these, you deal these into 25 new piles. And because there's infinitely many of these, you should have 25 piles of infinitely many notes. And my post-production people have told me that we don't need to acquire any more infinite piles of £20 notes. They can just duplicate them in post. And they say they can work, absolute miracles in post-production. They talked a lot about rotoscoping, cloning. At some point, they're going to stop and blend or something. I don't know what the point of that is, but they told me they're going to do some pretty spectacular effects over here. So now you should be looking at 25 piles, and it's the same number of notes. An infinite pile dealt out into 25 infinite piles. Same as this. So now every single layer has one note on this side and 25 of those across all the piles, so that they're worth the same. And that's both showing us, first of all, that we can match these piles up to say that each layer is the equivalent value. So if they're all infinitely many layers high, they have the same value. Also kind of shows us that multiplying infinitely many notes by any finite number is meaningless, because you can just deal these or collapse them up into as many or as few piles as you fancy. My only issue with that analogy is the act of dealing. You're only going to finish dealing after you've done infinitely many deals, and that's only going to be true in the limit. It's going to take a very, very long time, and we need to be careful when we talk about infinity, because often you're dealing with limits, and you could as a better way of thinking about that. Start with the complete stack of infinitely many bills, and then just imagine every 25th bill sliding out into different piles at once. That's better, because then you'd straight away have your infinitely many bills in the 25 different piles. And actually, originally, when I was planning this video, I thought it'd be quite funny to have 2 infinite money guns and just be like shooting an infinite number of bills from each one. And then I realized, well, that doesn't work because you need to be doing it for an infinite amount of time. And that's going to take a really long time. I'd get pretty bored doing that. So instead, I've gone for these infinite piles. So they're all just here straight away, infinitely many of them, much better. Still quite expensive.
Right answer is yes. It's opposite to multiply them to 0. None of the $1 bill are exact the same as none of $20.
20 times infinity equals 1 times infinity, all divided by infinity. 20 does not equal 1. Thinky face emoji. I stay on the safe side and take the infinite amount of 20s.
They're dividing by infinity. Well, they're trying to divide by infinity. Why are they doing that? You can't divide by infinity. If you do, nothing makes sense anymore. Everything breaks and is just cut adrift. You can prove anything equals anything. It's because infinity is not a number. People are acting like infinity is just the biggest number. Like you have all the numbers, 1, 2, 3, 4, and you count and you count and you count, and eventually numbers are just like, I can't even, and they stop. And then after that is infinity, way at the end of the number line. But it's not. Infinity isn't the biggest number, it's a measure of how many numbers there are. Infinity is the whole number line. It's the size of the set of numbers. And because it's not a number, you can't do arithmetic with it. You can't divide by infinity. Which now brings us to the main event. See if you can spot a pattern in these comments.
But some infinities are bigger than others.
Some infinities are bigger than others. Not all infinities are the same.
Nah, because some infinities are bigger than other infinities.
One just feels better than the other.
Wrong. Some infinities are larger than others. You have real infinities, and then you have the complex infinities that go beyond human comprehension.
And people seem pretty obsessed with a specific video.
Hey, Vsauce, Michael here.
Hey, Michael, Vsauce here. Check out Vsauce's How to Count Past Infinity. It's pretty interesting.
There's a video explaining the Banach-Tarski paradox derived from properties of infinity, which you might find interesting. https://www.youtube.com/watch?v equals S86-Z-C-BA-A.
The video, How to Count Past Infinity by Michael of Vsauce fame, came out on the 9th of April 2016, less than 6 months before the money meme. Interesting. Now, when Michael was working on that video, he actually gave me a call. He wanted to talk through infinity, make sure what he was doing was going to be correct and precise. At the time, I'd just written my book, Things to Make and Do in the Fourth Dimension, which has a whole chapter about infinity. And I tell you what, it's not often you get a phone call from a friend saying, hey, can you talk at length about a thing you're obsessed about at the moment? Good times. But one of the main things I emphasized in what became a very long but finite call was when you're talking about like there being infinite amounts of something, you've got to be very precise and say infinitely many, because the way you refer to infinity in terms of a size, not a number, you've got to be very, very careful. And to Michael's credit, amazing video. I think it's very accurate. I think it's very insightful. I think it's entertaining. I think it got a lot of people introduced to the notion of infinity. It's 18.1 million views as we speak. Amazing. And so then I was thinking, well, that's weird. If Michael did such a good job on this video, why are so many people confused about infinity when it comes to piles of money? And why are people blaming Michael's video? I think it's because, like a lot of things, people half remember stuff and they go off of feel and they're not sufficiently rigorous when they reapply those techniques or concepts. And this also applies to a thing called Hilbert's Hotel, which also appears. Is that door? I've just noticed, has that door always been there? That's weird. Can I give me 1 second here? I'm just gonna. Hilbert's Hotel is a hypothetical hotel with infinitely many rooms, and this is a thought experiment to help get your head around infinite sets and matching them up systematically, specifically matching guests with rooms. So you number the guests and they go into the same room that has their number, and the classic starting point is to have another batch of infinitely many but countable guests show up. Can you fit them in? Yes, you can. You get everyone who's already in a room to move to the room number that's twice their original room number. So whoever was in room 2 moves down to room 4. As they're leaving, the person from room 1 is going into room 2. It means everyone's now in an even numbered room, and then you put the infinitely many new guests in the odd numbered rooms. It's a nice visual but yet systematic way to show that the infinite set of infinitely many even numbers and infinitely many odd numbers are themselves the same size as having infinitely many numbers. It's the same infinity, and that's the irony about this whole thing. All these videos with Hilbert's Hotel treat it really well, and the point they're making is these infinities are the same size. So you can actually check out a much older video that Vsauce did many, many years ago, and about a year ago on Veritasium, Derek did a short, nice animated video about Hilbert's Hotel. I like some of their matching functions. It's very cool. You can see those, but I think they're a great explanation for why these infinities are the same. So why are people getting so upset about different sized infinities? Wow, okay, so that was a thing. But the point is, people are aware of this notion that there are different sized infinities, and then when they come across an infinite set, they're not careful enough to see if you can match it up to the countable numbers to see if it's the same as the countable infinity or if it is genuinely a bigger infinity. And I guess the real issue is just that doing that matching process is often a little counterintuitive. You've got to be real systematic. It's not always obvious. I can demonstrate that with a semi-famous puzzle about infinity. This is where you've got infinitely many, I'm going to use table tennis balls, and then you number them and you put them in a box. So this is table tennis ball number 1. And the only rule is whenever you put in a square number, you take out its square root. So I've put in 1, I'm going to take out its square root, 1. Now that only applies if it's a perfect square, so it's got a whole number square root. So when I put in 2, that can stay. And I'm going to put in 3, no problems. When I put in 4, however, 4 is a square number, so I put in 4 and I take out 2. And then I carry on. I keep numbering the balls, putting them in one at a time. And the question is, if I carry on doing this for the infinitely many countable numbers, once I've done all infinitely many of them, how many will be left? And the surprising answer is 0. Even though if you think about it, on every single step, I either put in a ball and take one out. So if I put in 9, I'm going to take out 3, or I put in a ball and leave it there. So I'm going to put in 10. So it's always either staying the same or increasing. Yet, if I do that infinitely many times, either leaving the total number alone or increasing it, it ends up at 0. And you're like, well, that doesn't make any sense. There's no way that can be how it works. And once again, we're being tripped up by our human intuition because, and actually I've kind of set this up badly because by doing this one step at a time, I have to do it infinitely many times. And as we established before, that would take a very, very long time. So actually I could have rephrased this to say, I put in the first ball at like 1 hour to midnight. And I put in the next ball when there's half as much time left until midnight. And then the next ball, half as much, half as much, half as much. That means when it hits midnight, we've gone through the infinitely many halves. And I mean, right at the end, it's going to be chaos. There's going to be balls flying in. There's going to be balls flying out. But we will have infinitely many steps. And then right on midnight, bam, empty box. And once again, we're kind of thinking of infinity as just a very, very big number. But that's not how it works. We could actually reframe this. It'll make a lot more sense. Like imagine, first of all, you dump in every single whole number at once. There's infinitely many of them in the box. And now I'm going to dump out every single number that can be squared. Well, that's all of them. You can take any whole number and square it. So now I dump out all of them at once. And by doing it that way, it's way more obvious that you end up with an empty box. So the issue is, if you're trying to work out how big an infinity is, you can't just jump to the first conclusion. You've got to make sure you think about it very, very carefully.
Technically, the infinite number of $20 bills is faster than the infinite number of $1 bills. Make it rain, asterisk shoots singles out of a confetti cannon, asterisk.
Yeah, but $20 goes to infinity faster.
And as we've seen from this meme, if people aren't careful, they get real emotional. And actually one time, many years ago, I went on the BBC Radio 4 program More or Less, and I happened to talk about infinity a little bit, I think in the context of prime numbers, and people were upset. I got an official complaint registered against me.
I caught the sound of a man airing the preposterous notion that the sum of all primes approaches infinity.
They were very upset. But it's true. And I can see where their logic's gone wrong. It's like the square numbers again. You're like, well, there are fewer square numbers than whole numbers as you count up systematically. So therefore, there must be a different sized set of numbers, just like not all numbers are prime. There are fewer primes than numbers, but you can put all the primes in order and number them. And so we get bogged down in thinking about it in terms of counting up gradually, and we shouldn't be doing it that way. We should be thinking about the whole set at once. Infinity is not a process where you count and count and count and count and eventually get there. It's a process of looking at all of it at the same time. So what is a bigger infinity? If they are different sizes, what on earth is bigger than the countable numbers? And it's not fractions. It feels like it should be fractions because you've got your whole numbers, 1, 2, 3, 4, and if you pick any two of them that are next to each other, there are no more in between. Like, that's it. They're spread out. Whereas fractions, you pick any two fractions, there's always another fraction in between. You're like, now we got it. There's more of them because as you zoom in, there's always more and more and more. It's not just the number line going out. However, if you're very careful, you can arrange the infinitely many fractions to assign them an individual counting number each. I did a video years ago about the Stern-Brokat sequence, which is my favorite way of doing that on Numberphile. You can check it out. And there are other great videos that show you how you can number the fractions. Where you can no longer number it is once you hit the reals, or rather, numbers that have infinitely many values in them. So I tend to use the reals to indicate that because you've got infinitely many decimal places. In Derek's Veritasium video, they had people arriving at Hilbert's Hotel whose names were an infinite string of A's and B's. A very nice way of doing it. And because you've got infinitely many digits, let's say, per item, if you go through and number them all, you can use a clever process. You have a diagonal argument where you generate a new, importantly, infinitely long number that is nowhere on the list. It's that infinitely long that's important. I've had people email me and say, well, hang on, the integers have infinitely many lead zeros. And that's true. They do have infinitely many lead zeros. But you can't use them because every counting number is finite in length. No matter how far you count, how far you go down the number line, how big your integer is, they're always a finite length. There's no infinitely long integer. And so it means you cannot use infinitely many lead zeros or change them to make a different integer. The reals work because there are infinitely many decimal places trailing off, and you can mess with them. Whereas fractions, yes, they may repeat, but you can represent them as a finite number. And so it's difficult to grasp, but there are loads of other great videos out there that show you this diagonal argument. And once you have these reals, that is a bigger infinity. But is it the next biggest infinity? We have the smallest infinity, the countable numbers. We've got the reals, a bigger infinity. But is it the next one up? Is there an infinite set that's got a size that's between those two? Well, not only do we not know, we can't know. It's provably undecidable based on, I say, our current mathematics, which is not to mean what we currently understand, is to mean the axioms we're currently basing all of maths on, which means the question of what is the next biggest infinity after the countable numbers doesn't really make sense. You can either add axioms that force it to be the next biggest, or you can add axioms which force it to not be the next biggest. It's really annoyingly not even a sensible question to ask, which I find absolutely mind-blowing. I find it almost more amazing than the fact that there are infinitely many different sized infinities. Let's not go down that path. I find it even more incredible that the notion of ordering them to know which the next biggest is doesn't even make sense as a question to ask when it feels so sensible. It's not math. Trademark. In conclusion, same amount of money. If you're new to the channel, thanks for watching a whole video to get a very thorough and meandering, self-indulgent answer to the meme. Same amount of money. Although I like the fact I started with the meme and ended up ranting about the continuum hypothesis. More about that online and in my book, Things to Make and Do in the Fourth Dimension. I'll link to it below, of course. Huge thanks to all my Patreon supporters, people who watch all these videos all the way to the end. Thanks for hanging around. Thanks to my Patreon supporters, all this money was possible. That's such a great sentence. To say an extra amount of thanks, because I am infinitely grateful. I'm infinitely many gratefuls. I have printed out every single Patreon supporter on a piece of paper that fits in the money guns. I've replaced all spaces in your names with underscores. That's because I was doing this quickly in a Word document. I didn't want some people's names to wrap off one note onto another one. And I've replaced all letter S's with $2 signs, because I think that's hilarious. And I'm going to end the video by shooting all of these names out of the money guns. If you were supporting me on Patreon a week before Halloween, your name is definitely in here somewhere. You may or may not be able to see it. That's the nature and excitement of the money gun experience. I will also say very quickly, if you want to get involved in whatever ridiculous thing I do for my Patreon supporters for Christmas, you need to be supporting me by the end of November, because then that's when I start working on Christmas plans. So if you want to get involved, if you want to get the physical card, etc., make sure you're at the tier that you want on Patreon. I'll link to it below. But now we end some money gun action.